Hello everyone. So in the last class I had asked kindly try to do these two things. I start with the second one. I will try to give a few examples on Skew Field. So first thing is, let me try to solve this. Solution is, what is a skew field first of all? A skew field is, or else a division ring is, a ring with unity in which every non-zero element has a multiplicative inverse. That means if I include commutative property, it will be a skew field. It will be a field. That means if I just think about the Venn diagram of the field and the skew field, field is contained in the skew field, because putting more conditions, imposing more conditions on the algebraic structure, it will shrunken. That is the idea. So field will be there. So it has additional one property, that is a commutative law. That means because of that additional property, it will be smaller than the skew field. So every field is a skew field. Is it clear? Very trivial example. Observation. Any field is a skew field. So you can give ZP, where P is prime, Q, R, C, and give this. Is it fine? Again, you can give few examples, particularly because it satisfies more properties. If you ask me, sir, this and all will satisfy commutative law, give me an example that doesn't satisfy commutative law and it just fits in this, not here. It will fit here. Is it clear? So what else I gave, those and all are fetched from this. But what will be the situation here? How to think about that example. So I will try to give you that example. So it's denoted by h of r, or else sometimes we will use in short h itself, which is an 4-dimensional vector space over R. So it's an 4-dimensional vector space over R. In the sense, it will have bases, 4 elements will be there in the basis, denoted by 1, I, J and K. And if I say it has 4 bases, I can write that space by 4 linear combination of these 4 elements. That is, I can write it as A, that is 1 into A, plus B into I, plus C into J, plus some D times K, where A, B, C, D are taken from the real field. And how the addition and multiplication is defined here. See, addition is defined to be, as usual, we will add component wise. Is it clear? So if I have A1 plus B1I plus C1J plus D1K plus some other component A2 plus B2I plus C2J plus D2K, the addition is defined to be, it is A1 plus A2 plus B1 plus B2 into I, C1 plus C2 into J plus d1 plus d2 times k. So addition is defined to be this, and it's an abelian group in fact, because it satisfies all the properties, and the identity element is 0 plus 0 times I plus 0 times j plus 0 times k. So it will be an abelian group, and you can have a additive inverse also. If this is the element, I can find minus a1 minus b1i minus c1j minus d1k. That is possible because these are real numbers, so I can find the negative of that real number. Is it clear? But how the multiplication is defined? Multiplication is defined to be I square, it's equal to j square, which is equals to k square. That will give me minus 1, and I into j is given to be k, and j into k is given to be I, and k times I, it is given to be j. It's in symmetry, I, j and k. I goes to j, j goes to I, j goes to k, and k goes to I. That's what I had written. I times j is k. Then I just permutate them in this way. I goes to j, then j goes to k, j is coming to k. I am taking the next one. K is coming to I. Here j, if I apply one permutation, j will go to k. K is there. If I apply one permutation, next fellow is I. Is it clear? K goes to I. So I goes to what? I goes to j here. So I will go to j. And this is equals to, this is interesting, this is how the multiplication is defined. Okay, this k is minus j times I, and this is minus k times j, and this is minus I times k. This is how the multiplication is defined. Is it clear? So you can take any element. If I take some q equals to a plus bi plus cj plus dk, and q dash equals to a dash plus b dash I plus c dash j plus d dash k. You can take like a1 b1 likewise also. So if I find q dash, it will be a plus bi plus cj plus dk, and a dash plus b dash I plus c dash j plus d dash k. Now a times a dash, a dash. Then again, if I multiply this, this will be minus b dash, because I into I is minus 1. Similarly, cj c dash j is minus cc dash, j into j is again minus 1, minus d dash. Likewise, if I equate the coefficients of I will get ab dash, ba dash, cd dash minus dc dash into I plus ac dash plus ca dash plus db dash minus bd dash into j. You kindly try to do this. It's easy. Just multiply and just equate the coefficients of I. That's all. Then multiply and equate the coefficients of j. Then just sum up all those things. Here it is ad dash plus da dash plus bc dash minus cb dash k. So here H is a ring with identity. H with respect to addition and multiplication, how we defined, is a ring, and it's a ring with identity, and every non-zero element is invertible. If A is assumed to be, let me assume Q is A plus Bi plus Cj plus Dk, it's an element of H. such that this is non-zero. Then how does Q inverse will look like? See, it's very interesting. Just take the conjugate of this. That is, A will be as it is, minus Bi minus Cj minus Dk by, take the modulus of everything, A square, B square, C square, D square. So every non-zero element is invertible. So this is the inverse. So if I multiply Q inverse, I will get 1. But whether it is commutative? No, because I into j is not equals to j into I. Why? Because I into j is k by the definition. But what is j into I? J into I is minus k. Is it clear? Because k is minus j times I, multiply by minus sign, minus k is j into I. So I into j is not equals to j into I. This is not commutative. So it's an example of division ring. Is it clear? Every field is every field is an example for division ring, but it's an exact property where it doesn't satisfy the commutative law. Is it clear? So then again, I had posed one more question. The question is, this show that every non-zero element in Zn is either a unit or a zero divisor. First, let me try to think about an example. Let me consider Z6. Now, I will consider 2. 2 is non-zero, whether it's a zero divisor or not. So 2 times 3 is 6, it's a 0. So it's a non-zero, but the product is 0, means it's a zero divisor. So it's a zero divisor. How about 3? 3 is also a zero divisor. How about 4? 4 times 3 is a zero divisor. Is it clear? How about 1? 1 into 2 is 2, non-zero. 1 into 3 is 3, non-zero. 1 into 4 is 4, non-zero. 1 into 5 is 5. So it's non-zero. But whether it is a unit, that means whether it is invertible. Invertible in the sense I need to find the multiplicative inverse for it. So 1 times 1 itself 1. So it's invertible. It's a unit. How about this 5? See, 5 is also self-inverse. So is it clear? So it has inverse. So it's left alone. This cannot be, these 3 cannot be the inverse. So it's the inverse of 5 is itself. 5 into 5, it is 25. 25 is congruent to 1 modulo 6. So 5 is the self-inverse. So 1 and 5 are self-inverse. So if I pick any element, non-zero element, that's what I stress this. I didn't consider 0. Because 0 is always a zero divisor. Is it clear? Now, 1 is there. I took 1. It's an inverse. It's a unit. I took 2. It's a zero divisor. I took 3. It's a zero divisor. I took 4. It's a zero divisor. 5 is again a unit. So you pick any element. Either it will be a unit or else a zero divisor. So simple. We need to prove it. That's all. Whether it's clear? Okay. Now, let me try to show this. So I'll just write it as the proof of this theorem is consider any non-zero element. So I am not considering this. I will consider the non-zero elements. So let I bar belongs to Zn be a non-zero element. If it's a non-zero element of Zn, and I will say let the GCD of I bar and n, let it be D. Let the GCD of, let me say I and n, because I bar doesn't make any sense. GCD of I and n is D. So here I can say GCD of 1 and 6 is 6, 5 and 6 is again 1. Is it clear? They are relatively prime. In that sense, so now we need to think. So these are 1 and 5 are relatively prime to 6. GCD of 1 and 6 is 1. GCD of 5 and 6 is 1. But here we can find GCD of 2 and 6. 2, 3 is 6, 0. So I left with 2. So 2 is the GCD. Likewise, there will be one GCD. Is it clear? So how to think about this? If I and n are, this is always possible. So I can write it mathematically defined. Now what? This D can be 1 or else it can vary from 1 to n. So first case is if D is equals to 1, what will happen? That is, if D is relatively prime. Here 1 and 6 are relatively prime, it was a unit. 5 and 6 are relatively prime, it was a unit. So now if D equals to 1, that is I and n are relatively prime, then what will happen? If they are relatively prime, I can find any positive integer, let me say s and t, such that the linear combination is 1. Now take the congruence. So I will have I bar, s bar. N bar is 0 in Zn. So plus 0 bar equals to 1 bar. That is I bar into s bar is 1 bar. That means inverse of I is s. Is it clear? So I bar is a unit. So that is I bar in Zn is a unit. So first thing is over. Next thing is when it will be 0 divisor. When it will be 0 divisor. So second case is I am not considering D is equals to 1. So I will just say if D is greater than 1, GCD is greater than 1. Likewise, if the GCD is 2, something likewise. So if D is greater than 1, then 1 is less than n by D. Definitely if I divide, since D is greater than 1, this will be less than n. If D is equals to 1, n by D is n. Is it clear? So what is I times n by D? I times n by D is I by D times n. Now you should ask me the question whether D divides n, sir. Yes, exactly. D will divide n because D is the GCD of I and n. So D should divide n and D should divide I. So D will divide n. Now I changed this. So will I get the fraction? No, I will get the integer. Why? Because D will divide I also, because D is the GCD. So here I will get an integer. Is it fine? Simply we cannot change. So here also it's an integer. But what is this? What is I by D and n? Now the question is, if I apply the modulo, this is congruent to 0 modulo n. Why? Because this is 0. That is I times n by D is 0. But I already assumed it's non-zero. So this is not equals to 0. This fellow is non-zero. But what about n by D? N by D is an integer which lies between strictly 1 and n. This cannot be 0. But their product is 0. Then I can claim this is a 0 divisor. These are 0 divisors. That is I bar is a 0 divisor. So both the cases I proved. First I assumed if D is 1, I will get it's a unit. If I assume D is greater than 1, you can think about this. Then I will get I bar is a 0 divisor. So try to think about the construction of the proof. Simply we cannot just think about all these things. First you should know this concept. Why I took this. So example is this. All at once you cannot expect everything should be fine. First you think about this example. Observe it carefully. Observation, you can put it in a mathematical way to prove a result. That's all. Is it clear? This works for any n. In that sense, we say it's a result. Is it clear? Okay. Next, moving on to, we'll prove one problem. This is interesting. If problem, in a ring R, if a square is a, show that R is commutative. Commutative in the sense, commutative with respect to multiplication. Because with respect to addition, it's over. It's an ended story. Because already we know it's an abelian group with respect to addition. So there is no point in proving it's commutative with respect to addition. We are more concerned about the commutative law with respect to multiplication. Because we are not sure whether it will agree or not. Okay, proof. Try to understand this. So given, let me say if a is an element in the R, given a square is a. But what is this a square? Can I write it as a is a square? What will be minus of a whole square? Still it will be a only, because minus a times minus a. But he has given a square is a. So minus a square will be minus a. Is it clear? Or else put this is b square equals to b only. If I assume if b is in R, b square is b, put b is equals to minus a. So what is b square? Minus a whole square. What is b? It is minus a. So that's what I had written here. So a is equals to minus a. Keep this in mind. It will help us to prove the result. But what is a plus b? If a is in R and b is in R, a plus b will be in R, because it is an group with respect to addition. Closure law will hold. If a is in R and b is in R, a plus b will be in R. If a plus b is in R, what is a plus b whole square? It's a plus b. Now, what is a plus b whole square? It is a plus b times a plus b. Okay. So it is a square plus b square plus ab plus ba. You should not ask me to write, sir, a plus b whole square. From high school we had studied it as a square plus b square plus 2ab. What's wrong here? Why are not writing it likewise? The reason is, it's a ring. We don't know whether it is commutative or what. Whether ab equals to ba, we don't know. We are not sure about this. Because if I have a ring with with matrices, matrix multiplication is not commutative. I cannot write ab equals to ba. Is it clear? In that sense, I cannot write it as ab equals to ba. This will agree if ab is equals to ba. So now a square plus b square, ab plus ba is here. Now what is a square according to us? A square is a. What is b square? It is b plus ab plus ba. So by cancellation law, a goes with a, b goes with b. So I have 0 equals to ab plus ba. This will imply me ab equals to minus ba. Is it clear? Now, but now how to conclude ab is ba? Can I write it as b times minus a? But what is minus a? Minus a is a again. ab equals to ba. That is, R is commutative. Is it clear? Now, before I end up my session, I will try to give an insight, because proving many theorems without giving insights, it will be you will say, sir, what's the highlight of this today's class? So far we have studied ring, division ring, integral domain as well as field. Now question is, think about this. whether Z cross Z is an integral domain. Z cross Z is, sir, how to define this Z cross Z first of all? That is, it's a ring, I agree. It's also a ring, I agree. But how to say that some operation is defined here? How to say multiply them? So that is, if R1, R2, let me say Rn are rings, then is R1 cross R2 is a ring? Yes, it will be a ring with this operation. R1 cross R2 will be, it contains the ordered pair A1, A2, where A1 is in R1, A2 is in R2. How the operation is defined, how the addition and multiplication is defined. A1, A2, where A1 is an element of R1, A2 is an element of R2, plus B1, B2, where B1 is an element of the first ring, B2 is an element of the second ring. It is given to be, you should be very careful, this is an element of what? R1, this is an element of R1. So how to add them? A1 plus, it's an additive operation which is defined on R1 plus B1. Is it clear? I am writing plus subscript R1 because it's an additive operation which is designed for the ring 1. Again, A2 plus R2 B2. So this is how the operation will work. So this addition may be different, this addition may be different. For example, R2 may be a matrix and R1 may be integer. Then matrix addition is just, you will add the matrices, you know how to add the matrices. Here it's just an integer, addition of integer. So in that way it differs. But what is A1, A2 times B1, B2? It is A1 multiplication with respect to R1, B1, A2 multiplication B2, and this multiplication is R2. Here if I say, as usual, as I said, if I say this is Z and this is an matrices, then the addition will be this and multiplication will be multiplication of two integers. Here multiplication of two matrices. Is it clear? So this will form a ring. Likewise, now the question we can answer is whether Z cross Z is there, whether it's an integral domain. Whether it's an integral domain. So integral domain means what? We'll say it's a commutative ring with unity in which, it's a commutative ring with unity which doesn't have zero divisors. So don't worry whether it is commutative and all, whether it has zero divisors. Take two any non-zero elements here. If I multiply, if I get 0, it has zero divisors. For example, 1, 0 is here. Here you take 0 and comma 1. So this is a non-zero element. This is also a non-zero element of Z cross Z. I will say 1, 0 and 0, 1. Let me consider these two elements. Multiply them. 1, 0, 0, 1. How to multiply? First with this, then this. And multiplication is defined for integers only. So usual multiplication. 1 times 0 is 0, this is 0. Whereas this is non-zero and this is also non-zero, but their product is 0. If their product is 0, it has 0 divisors because these two are non-zero elements. Is it clear? Both are non-zero elements, but their product is 0 means it has 0 divisor, so it is not an integral domain. So if it is not an integral domain, definitely it will not be a field. Sir, if R is a field, or else let me say set of all real, or else fields, that is real field, consider the real field, what will happen to R cross R? Whether it will be an integral domain, because it's also an integral domain, this is also an integral domain. In fact, every field is an integral domain. That's what we had proved. Whether this will be an field or else it will be an integral domain, need not be. Consider same example, 1, 0, 0, 1. These two are non-zero elements in R cross R, but their product is 0. So it's not an integral domain. Is it clear? In general, you can say for any field. Is it clear? It's not an integral domain. So it's not R cross R. Let me write it in observation. Observation. R cross R is not an integral domain. So it cannot be field. This implies it cannot be field. Why? Because if I say it's a field, it will be an integral domain. That's what we had observed. If it's a field, that will imply me it's an integral domain. I'm saying it's not an integral domain itself. If I say, for example, on contrary, let us assume R cross R is a field. By this result, what else I can claim? If it's a field, I can say R cross R is an integral domain. But it is not an integral domain because it has 0 divisors. That means I assumed what else I assumed is wrong. That is, R cross R is not a field. Similarly, C cross C is not a field. Is it clear? So, however, with this, I conclude my class. And in the next class, we study about subrings and its properties. You can refer some of the references, what else I had advised you in the first video. So, and Ramitan Foote is good. Gillian is good, and you can refer Indian author books also. Gopal Krishna is there, N.S. Gopal Krishna, and Freilich is there, Einstein is there. You can refer them also. But however, just think about what are subrings and few examples on that, and try to think about ideals. What are ideals? What is the relation between subrings and the ideals? With this we conclude. Thank you for watching.